This lecture focuses on biostratigraphy, the process of using fossil ranges to subdivide rock units into time bins and to correlate those rock units between different localities and regions. The geological timescale that you're familiar with was developed in the 19th century primarily based on fossils and based on biostratigraphic correlation long before the absolute ages in millions of years were actually known. So the periods like the Cretaceous or the Permian are well known, and you're likely familiar with this geological timescale, but there are actually finer subdivisions within those periods as well, also based on their fossil content. So those finer subdivisions called stages can even be further divided into zones or even subzones using specific fossil groups called index fossils. The example at the bottom illustrates ammonite zones and subzones on the right for the Toarcian stage, which is part of the early Jurassic. There are also other zonations for the Toarcian using different groups of index fossils, for example, calcareous nanofossils. So there are a number of ways to define a zone. It can be based on the range of a single species, the range of co-occurring species, or maybe the abundance of a species, for example, the Acme biozone, based on the time when a species is particularly abundant. But the most common method uses the first appearance of a chosen index species. For example, the base of the Capitanian stage in the Permian has its global definition based on the first appearance of the conodont species Gynogondylella posterata, actually at a specific site in West Texas. So what makes a species a good index fossil? Well, first, it should belong to a group that evolves rapidly so that the species have shorter durations. Shorter durations permit subdivision of geological time into shorter intervals, which is better for high-precision correlation. Second, index fossils should be abundant. Correlation is one of the important goals of biostratigraphy, so abundant fossils are more likely to be found reliably in multiple places. Third, an index fossil, or a good index fossil, should have a global, or at least a very widespread distribution to allow correlations between different places and regions. Well, truly global distributions don't occur. As the lower left illustration will show, it shows the range, or the typical range of a couple early Jurassic ammonite families. The Hildosera today typically occur at lower latitudes, whereas the Amaltheids occur at higher latitudes. So as a result, there are two parallel zonations in Europe, one in northern Europe and one in the Mediterranean region of Europe, that must be correlated to each other. So fourth and finally, the species should be found in a wide range of lithologies representing a variety of environments. So that also isn't necessarily true for some commonly used index fossils at least. For example, graptolites are primarily known from shale-dominated and often deeper water successions and are rare in shallow water sandstones. Subdivision of the geological timescale is an important outcome of biostratigraphy, but correlations of events between different regions is really perhaps a more important goal. For example, it can aid in exploration for petroleum or mineral deposits that are of a known age in one region. By looking in the other region at rocks of a similar age, you may be able to find those resources. It also allows recognition of ancient global or environmental or climate changes that you might want to look for similar environmental changes in different parts of the world. So correlation on the basis of fossils uses the principle that the first appearance datum, or the FAD, occurred at the same time, at least geologically speaking, worldwide. However, that assumption of synchroneity may not be true for a variety of reasons. First, the observed fossil range of a species is always less than the true range of that species. If speciation occurs in small populations, this means that the species is likely to be geographically restricted when it first originates and later spreads to other regions. That time gap may not be significant geologically speaking, but it could also be. It's difficult to tell. Sampling is, of course, also incomplete, as illustrated in the graph below. The left panel shows the true ranges for some hypothetical species, and the right panel shows a modeled fossil record, which you can see includes many gaps. The gray shows the true range, but the black dots are where they were actually sampled. And this is with 10% sampling efficiency, which is probably an overestimate of how well the record is for certain rare groups. Finally, taphonomic losses may also introduce additional gaps as the species, especially rare species, may not be preserved at all in certain units. So because of these sampling effects, the lowest recovered fossil will always be younger than the true first appearance datum or FAD. The bias, or the distance between the observed occurrence and the true first appearance, will be larger for rare taxa, which have more and larger gaps in their record, and those rare taxa may also be lost altogether. Well, even if sampling is complete, the sedimentary record still contains many small breaks or gaps. They range from frequent and short gaps, such as between each bed in a shallow marine succession, to longer but less frequent gaps that are recognizable as unconformities. In the example sections below, there are gaps in sections 1 and 3, so no sediment was deposited, or if it was deposited, it's no longer preserved during the FAD of our particular species. So as a result, the observed first appearance in columns 1 and 3 is separated even more from the actual FAD when there are those gaps. And even if there is continuous sedimentation and complete sampling, the preservation or collection of certain index fossils, at least, often depends on the lithology or the environment. So that's called a facies bias, because facies refers to the complete lithological and environmental features of a rock unit. In the case of graptolites, for example, which do not preserve well in coarser sandstone due to their non-mineralized skeleton, they will have a larger gap between the observed and the true FAD in column 2, because column 2 does not contain suitable facies for their preservation at the true first appearance. You see, the graptolites show up pretty quickly once you get black shale with favorable facies for their preservation, but are not present in the coarse sandstones. In addition, as you know, organisms have preferred environmental tolerances, so therefore they have preferred habitats, especially in response to depth-related parameters like substrate and energy levels. This can be visualized schematically as a model where the species has a preferred depth, the peak of the bell curve, as well as a depth tolerance or range, which is the width of the bell curve. The height of the curve represents or depends on the abundance of that species. So some species like A in the bottom panel have very broad ranges so that you're likely to find them or moderately likely to find them in many different water depths. But others like species C have very narrow ranges so you're extremely likely to find them at their preferred depth but really not anywhere else. So therefore the probability of collection depends on the depositional environment or the facies at each position when you're sampling in a succession of rocks. This is important because facies at a section are often cyclical as a result of changes in base level, which is a function of sea level and tectonic subsidence or uplift. This photo shows different levels of cyclicity in one of these successions. This is a carbonate or limestone-rich succession. There are smaller cycles marked by the red arrows that transition from finer-grained and more recessive beds to a cap of more resistant, coarser-grained limestones. There's also an overall shift from the bottom of the section to the upper part towards coarser-grained, more resistant limestone cliffs. So that combination of species-specific habitat and often depth preferences with cyclical changes in the depositional environment produces non-random fossilization. In the model illustrated at the bottom, some species have preferred depth in deeper facies and others in shallow facies, and water depth changes cyclically. So as a result, the rapid transition from shallow to deep facies at horizon 40 produces range truncations where many of the species with shallow water preferences are found quite commonly in shallow water, but are not found in the deep water facies, even though they should still have been present on in the world somewhere. Similarly, the observed first appearances of shallow water species will also be biased if that species truly appeared when the succession that we're looking at was represented instead by deep water facies. So to sum up, correlation is really an important goal of biostratigraphy, but it's also critical to assess sampling effects, look for sedimentation gaps, as well as determining habitat preferences and the effects of changing depositional environments when you're trying to correlate observed first appearances between different sites.